Hello, everyone. Welcome to the next seminar in our webinar series. Today, it's our great pleasure to have with us Professor Steve WaiChing Sun from Columbia University. Professor Sun obtained his BS from UC Davis, MS from Stanford, and MA from Princeton, and then his PhD from Northwestern. Prior to joining Columbia, he was a member of the technical staff at Sandia in Livermore, California. He's received numerous awards, and to mention a few, these include the NSF Career Award, the US Air Force Young Investigator Award, the Dresden Fellowship, and numerous others. Professor Sun's research broadly are in the mechanics and physics of geological and porous materials such as rocks, soil, concrete, and salt. And his group specializes in creating and deriving, implementing, verifying, and validating different kinds of theoretical and computational models for engineering applications connected to these kinds of materials. So without further ado, let me hand over it to Professor Sun. So thank you so much for joining us, Steve.
Yeah, thank you. Thank you so much for the introductions and the invitations. So today, I would like to take this opportunity to provide some update on our work on geometric learning for constitutive modeling. Basically, for more precise or complicated constitutive modeling, if we need to get something that are very precise, if we want to create predictions like digital twins that are very accurate, we want to explore whether this is possible. If not, what are the things that we can learn using the assistance of machine learning. So before I get into the details, I'd like to thank the contributor. They actually each contribute a part of the talk. Nick Venice, who I think is in the audience, is working on the graph embedding for generating internal variable for plasticity. Ming is working on the geometric part of a yielding manifold, and Q Yan is actually working on the deep reinforcement learning on the design of experiment. We probably cannot go into very deep in all of these topics, but I'll try my best to keep an overview with some sufficient details that would be helpful. The graph embedding paper are currently in minor revisions, but then the geometric pi paper is already available in CMME. So if there's interest, I'm happy to share the paper and all the details. So the first questions we want to ask is that how do we use machine learning to write a precise model, or put it another way, and that is not very realistic. If I actually have infinite amount of data, is it possible to write a highly accurate, precise, and robust model? And I would use the plasticity problem as an example. In plasticity, one aspect of writing plasticity model is to write U functions. This is a very simple task, but at the same time, very complicated. U functions basically is criteria that tell us the boundary between a material being a path independent and path dependent, and they are mostly expressed in terms of stress. So I'm just taking that as an example. In the last 100 years or so, we keep proposing a lot of U service, and they all involve some kind of manipulations on the geometry in the parametric space. One measures, if we plot it in the principal stress space, we can get cylindrical objects, the Zuckerberger, a cone. Gerson's is actually ellipsoidal objects, Trasker, Mock Coulomb, boson. There are many other problems. The thing that we would like to ask is that a very simple questions. If I have different data, and then I may not necessarily need to explain the physics, but I simply want to create an arbitrary complex U surface. Is it possible? Okay, so in this case, it seems pretty, in all those cases in the past, what actually happened is that we create a mathematical representations of those equations. Okay, we can think about ourselves as a human symbolic regressions user with some explanations of the physics. But there are scenarios that make this approach where we try to come up with a mathematical equation to describe the model very difficult. And they are related to the dimensions. All those materials that are shown before assume isotropic behavior, and so the stress can be sufficiently represented by the eigenvalue of the stress tensor, which is actually the principal stress. But if you don't have any symmetry, you are dealing with at least 6-dimensional components of the stress to create these criteria. And if you have the size effect, then we actually need to include a higher order effect. And then we also need to think about how to evolve the history dependency in terms of the internal variable. I just want to show an example of a recent work we did with the micropolar U-surface. We have a direct numerical simulations model that we are using to homogenize to get a microscopic U-surface. And in this material, we have the classical string mode, kinematic mode that actually create a stress, but we also have a non-conventional stress called a couple stress that are related. The tractions of the couple stress is related to the moment divided by the area, not the force divided by the area. And you can see the complexity when I deal with that 6-dimensional space. This is not even the micromorphic that show here, just the micropolar. You can see that when we want to do simply a regression in such a high-dimensional space, it becomes increasingly more difficult. Okay, so one may say that a curve fitting in 1D probably doesn't need a machine learning, but in such a high-dimensional cases, how do we create the right geometry is actually necessary, and how do this geometry affect the physical response is also another important thing that we would like to explore. But what it transpires is that the necessary conditions to create those mathematical model is to able to find out what is the right way to represent the geometry and the resolution of the geometry that give us all the material model in the right parametric space. This is actually a very old problem. If you look at the old paper by Professor Jim Rice, there are multiple issues in this. One is to create a U-surface. Another one is also in the revolutions of those U-surface that give us the stress string response. We typically using it by creating a kinetic law for the internal variable, and the internal variable will represent some kind of microstructure rearrangement. The issue is that typically those rearrangements are not describable, and we actually don't know how do we actually connect the internal variable revolutions with the internal arrangement that give us the physics. In very limit case, for example, a plastic slip, we can actually observing that and we can relate that, but in general, it's really hard to doing it. So in a classical constitutive model, we were actually relating those with some known parameter that we consider is very important. For example, the void ratio, porosity, fiber tensor, and then we try to cook up something so that the U-surface is evolving along with those important physical descriptors, such as dislocations. Okay, but then what we actually want to explore is the following. If a material is deformed in a way that we don't know what is the right vocabulary to describe it, or what is the geometrical measure or whatever that allow us to do it, then we don't have the vocabulary, and hence there's no way we can connecting them. So this is where the machine learning can play a role, in my opinion, to create those descriptors that can be connected to the microstructure revolutions and help us understanding the mechanism of the material, the homogeneous macroscopic response coming from the small scale behavior. So here I would first address the first questions, which is the following. Okay, if I have a very complex material, can I actually properly define the U-surface? Okay, in arbitrary dimensions. That seems to be a very easy task, but then if we actually do have a very complex behavior, we do need to have the capacity beyond dreaming up of particular equations. So here we would actually prescribing the yielding in the stress space and then using the Riemannian manifold to actually allow us to define the yielding. The reason is that this would give us more ability to manipulate or to control the complexity. In a Riemannian manifold, we are assuming that there is a tangential space in which is also equipped with the inner product. So locally, if I actually look at the point, you can get the tangential space that are linear. What actually we want to do in the machine learning is something very simple. Imagine that I have a spherical object, and then I actually try to connect it with a lot of local space that are actually curved. I just simply want to connecting them together so that in the individual point, I can actually using the local parameterization to prescribe the yielding. Okay, so this is different than the global approach where we try to come up with one U surface to cover the entire space to describe the yielding. Okay, and it's also different than the classical U surface in the sense that we are not trying to prescribe or predict the yielding explicitly, implicitly using an implicit function, but directly mathematically represented as a manifold. Okay, so we need to introduce some terminology. Basically, we need to in this case, what the machine learning did is actually to learn a mapping. If you work on finite element before, you probably will recall isoparametric mapping. Here, the thing is not exactly identical, but then probably you can say you get the inspiration from it is that we want to have some measurement in which the material is initial yield, and what we want to do is to create those patch and then try to deform it in the stress space in the possible way so that they are actually matching all the point cloud that we obtain from the stress measurement that detect the yielding. Okay, so in particular, what we're trying to create is those local mapping that can allow us to describe the yielding, and then we want to connecting them so that it can form an atlas that are actually consistent with each other. And this would be the alternative approach to allow us to define the yield surface. And what we actually want to show is whether this really complex approach is necessary or not. And if we're actually using this, what is the benefit? In this particular case, what we actually want to answer is that if I actually change the microstructure, how would the corresponding yield surface actually changing, and whether we can predict the revolutions of those yield surface? Okay, so from a procedure perspective, I would actually explain what they did here. Okay, imagine that the true answer is just a 1 meter's yield surface. That would make this approach completely unnecessary, but let's, for the argument's sake, we want to do that. Then if we measure the yielding of a 1 meter's material, we will get those point cloud that are actually on the cylindrical object. Okay, we can actually partition those point cloud using a Poisson sampling desk to actually partitioning them. And then we can learn the local coordinates chart mapping one by one to form a local patch. And then the final machine learning procedure is to make sure that in the overlap regions, the two patches are actually consistent to each other. This is actually the machine learning approach, in which case each local patch are actually trying to learn the mapping of the yield surface locally, but not globally. This could be actually helpful for a material that actually require different fidelity in different yield surface. But long story short, we did not do anything special except that we use the multi-layer perceptron that are overall parameterized. And we use specific distance measures. In the classical way to create a yield surface, we will use the mean square error. Here we use the synchron regularized distance that are coming from the optimal transport theory. There's an entropy term there, and we will see why this entropy term is actually useful. We try to feeding it, but we also want to allow some level of entropy, and this entropy term could actually help us to overcome the noise. We put it into the Chaska U surface, and we can see that if I actually purposely introducing the noise in the material, which in real life in experiment that would very well be happen, we can actually using this synchron regularization term to help us to obtain the good behavior that are actually stable. For associative flow rule, the U surface, the plastic flow, which meaning that the gradient of this U surface would be related to the growth of the plastic deformation. So if we can get a stable direction, this is very important to help us trigger the right plastic strain that are actually stored, that are actually triggered by the beyond the yielding. And here we can see that there's a good property in the sense that it filters the noise, but it also maintains the sharp feature of the Chaska U surface that we play with in that numerical experiment. As we mentioned before, in order to trigger, in order to create the right U surface, we also need to control the stress gradient for the associative flow rule, and this could create an easy way to incorporate with experiment. In experiment, it's almost impossible to measure the stress gradient, but we can actually measure where is the plastic strain by actually assuming an elastic model. So we know the plastic flow direction that could be measured and that could be incorporated in the training as well. We will add this term that are actually making sure that the predict plastic flow directions are actually aligned with the U surface. And this can provide another benefit in the sense that when we actually want to create a very complex plasticity model, a lot of time we will use a non-associative flow rule so that the stress gradient actually doesn't necessarily to be aligned with the plastic flow. So this is called non-associative flow rule, and that can actually lead to some thermodynamic inconsistency or other issues. But here, what we actually want to explore is the following questions. Perhaps we don't need the non-associative flow rule, is the lacking of the geometry, the ability to create a complex U surface that make it necessary to create a non-associative flow rule. Here, we also in the machine learning is trained in two steps. First, we actually ensure that the individual patch are actually trained properly, and then between the two patch, we actually need to have another training to make sure that in the two patch, they actually have a consistency between the two patch that are actually consistent with each other. Okay, so this would give us not just the good representation of the U surface, but more importantly, we found out that it turned out this could be have a benefit on dealing with a material that have very sharp change in the plastic flow directions. So we will introduce a closed point projections to deal with the non-smooth U surface problem. So this is actually the U surface. And then now notice that we no longer have a global U surface, but we have individual patch. Each patch have actually a center. When we actually try to introduce a return mapping to get the correct stress, we will actually run the algorithm with a try stress and we try to return it. In the classical way, this is not a problem, but in the Mach Coulomb plasticity, in the corner, because there's a two admissible pressure gradient, the stress gradient are bifurcated, and so this would need to the Newton-Raphson algorithm have a hard time to converge. But in the new approach, because we can actually conduct the local projection between the local patch and the tri-state, but not through the entire global U surface, we can bypass this problem by actually having the manifold projection directly onto the individual patch. This is actually one example of just a perfect plasticity Chaska U surface. We want to try the return mapping algorithm with the classical Newton-Raphson algorithm directly on the point where just a little bit outside of the stress gradient. not surprisingly, if I try to solving it in the standard Newton-Raphson's algorithm, the two intermediate solutions just keep iterating. This is actually due to the fact of the two stress gradient can lead to the Newton-Raphson's residual to just going in between the two patch. But in the projections on the patch problem, we can actually bypass this and then actually locate the correct U surface. You can see the iterations can be significantly reduced for the material that have a linear elasticity or have nonlinear. The key point is that this geometrical feature and the local definitions can help us bypass the iterations. Here we want to do another experiment. This is a soil model with a layer soil. This is not a real experiment, but actually pretty representative for the U surface that of a geomaterial that are anisotropic. So there's a two layer, and the red layer are actually the hard layer, and then the blue layer are the soft layer. We purposely using the circular domain, and we only do it in 2D. And then we basically generate a database of these material, loading it in different way. And then we actually want to know what is the exact U surface we have. And this is actually the 5 patch of this U surface. You see in the stress space of sigma XX, sigma YY, and sigma XY. You can see that surprisingly, the actual U surface that necessary to construct is way more complex than what we think, even though it's just a layer system. And if you look at the stress gradient, you will see the same. Okay, it's not like a circle. And you can also observe some sharp corner in the stress, some stress space, like in patch number 6, where you can see the intermediate change in the passing flow directions. And this could be explained by the pattern of the direct numerical simulations in the subscale. What we actually see, which is I think is pretty interesting, is that when the two passing flow are actually similar, the underlying deformation pattern are actually quite similar. This is actually the stress space loading it in a slightly different stress combinations on the same U surface on the different locations. And however, and you can actually also seeing that when the two U surfaces are similar, the underlying microstructure deformation are quite similar. However, if we actually have something that are very far apart, we can actually seeing that that the pattern actually could change quite a lot. We can also apply this. This is just another example on the HMX with a polymer layer for that are actually used for explosive. And in this case, in the 2D simulations, when we try to homogenizing it in that 5 patch, you can also see a different geometry that are actually pretty hard to parameterize it by hand. You can also see that for different state, the shape or the passing flow directions are actually constrained so that they are consistent with the U surface. So what we actually find out here is that the actual U surface, if you want to increase the quality of the predictions, or more accurately saying the precisions of the U surface, you require more advanced geometrical tools to create arbitrary objects that are actually representing the boundary of the path-dependent and path-independent behavior. And this manifold approach can provide a convenient way to introduce different arbitrary of complexity. The same thing can, in principle, apply for elastic energy functional or other type of material as well. Now, the second questions that we would like to tackle is that how do we evolve those U surface? Okay, if you actually know the material is U, okay, then but the material can also evolve when beyond the yielding. So how do we capture that? Okay, in a classical way, as we mentioned before, we're going to hook up some kinetic rule like the void ratio, like a Gerson model. We're saying that the U surface depends on the void growth, and then we try to come up with a story, and then that story converging it in that are confirmed by the observation that converge into mathematical equations. But let's just look at these two cases. Okay, so we have two particles. We have two granular ensemble that have the same void ratio but have a different arrangement. Or we have a two polycrystal that have the same average size, but then they are arranged in a different way. By intuitions, we know that the material model, if we're looking at it in a very precise sense, will be different, right? But how do we actually tackle those differences? Okay, so in the classical way, we need to introduce a new descriptor to describe the difference of it. Perhaps void ratio for C and D is not enough. We need to talk about how do we describe the fact that some of the voids are smaller, some of the voids are bigger. Maybe we need to averaging the size. Maybe we can introduce a coordinate number to actually describe the difference, and here, etc., etc. But what we are interested is to know whether it's a generic way to doing it from the machine learning. Okay, so this would be related to another type of geometrical learning, which is the geometrical learning on the graph. And graph is actually an old topic. It has been used periodically in mechanics. So this is just some example. In a polycrystal, you can represent a polycrystal as a wave graph where the particles that are connect together are connected by the edge, and individual particle are considered as a nodes. For the granular material, you also have a particle that could be considered as a node, and then they are connected. Or in some case, in a finite element simulations, you can consider the solutions of the finite element as a nodes, and then they are connected by the deformation gradient that are actually linking them together. So graph is everywhere. If you look at the social media, we can think our personal relationship with one another are also connected in a graph. Or where do we actually finish our PhD, which advisor we follow to could be also modeled as a tree. So, but here what we want to know is that if we can actually parameterizing or describing the microstructure as a graph, can I find a low dimensional description of this graph, and can we evolving it and put it into the constitutive law? So this is actually what we are trying to do. We want to changing from identifying individual physical descriptor to a machine learning approach to generate the descriptor, and we want it to be as interpretable as possible. So what essentially corresponding to mathematically is that we want to able to conduct a graph embedding. So what it means is that if I know the microstructure that I represent as a graph, can I actually map it into a vector space so that the graph that are similar would be remain close to each other in the embedded space, and then the graph that are very different would be remain far away. So this is actually what we did, and in machine learning, this is actually done a lot for other problems such as natural language processing. And in our case, we did not use anything really advanced for the graph embedding, but what we is going to use is a technique called a graph autoencoder. Okay, so this is the situations we are in. For example, if a granular material is deformed in the granular material could deform, and then during that, the conductivity graph would change, but then also the force will change. We want to parameterizing this microstructural evolution as a graph that are actually lower dimensional than the voxel by voxel representations, and then we want to embedding those graphs into an even smaller vector space to describe the motions. And this is actually just graph 101. So but what actually important is that in the very deep down of it, we need the following basic informations. We need the degree of the graph, which actually translate to what are the neighborhood, what are the number of the neighborhood that are put into the D matrix. We need the adjacency matrix that tell us which particle are actually neighborhood to each other. We can add a way there to actually talk about how important is that connectivity informations, and then for each nodes, we can actually put a feature on it to store the entire graph informations. So in this particular case, we have a 5 particles that are lumped together, and this particle are of different shape. So the shape descriptor would be actually put into the vector space to form the feature matrix, and then the adjacency matrix and then the degree matrix will give us the graph Laplacian as an additional input to the model. So here we want to consider the case where we are directly using the encode feature vector as internal variable. And what we actually want to do is that instead of directly, we will build a recurrent neural network to predict the stress from the strain. But what we actually want to do is that, do we think we want to evolving it by actually applying the microscopic strain and then see whether we can evolve the feature vector and from that predict the stress. You can see in this backbox approach, the predictions is actually quite okay. In a general case where you don't have a hierarchical data, and this could be very true for something, say, is homogeneous or something that doesn't inherently have a graph pattern, we can still use the graph as a way to represent the spatial informations, and from that we can compress the informations. Here is a finite element mesh, in particular a triangular mesh in 2D. So the gaseous point that are actually stored, the historical informations are actually at the center because this is actually a low order triangular element. If I actually look at how I would slightly abuse the terminology using each nodes as each gaseous point as a node of the graph, and then that would give us the graph. Now, if I actually deform the material numerically, I would actually trigger different equivalent passing strain, and that would be translated in the graph language, the way of the graph that evolve over time. Now, what we actually want to do is to introduce an encoder and the decoder to compress the informations, and then using that compressed informations double as the internal variable. So autoencoder basically is a neural network, specific neural network. So here we are not doing multi-layer perceptron, but just to illustrate the idea, we start with a bunch of finite element solutions that are actually constitute all the solution space. And we want to put it as an input, and then we compress the information into encoder into the latent space that are very small. And then we want to see whether we can actually train a decoder, the decoder part of the autoencoder, so that the input and output remain the same, but the latent space is much smaller. Okay, so in this particular case, okay, we would actually using the finite element as an example to demonstrate how to doing it for multi-scale homogenization problem with some microstructure. Okay, so the finite elements, each gaseous form will be the graph nodes, and then if they are connected with the adjacency finite element, that will form an edge, and then we will store the plastic string tensor as a weight, and then we're going to embedding it into a vector space. We will do the same thing like the general autoencoder, except that we would introduce a graph pooling step into the graph encoder. What basically means is that I'm going to learn the feature of the graph, and then at the end, I'm going to collapsing all the local feature, aggregating it. And then after that, I would just use the classical multi-layer perceptron to actually do the last leg of the data compactions to get the encode feature vector. This is two examples we try. There's a classical hole problem, and then there's another problem with void distributions, and then we collect a lot of finite element simulations to create a database that not exactly that large, but with 10 to 4 elements. And then what we actually want to do is to see whether we can actually predict the revolutions of the new plastic strength revolutions. So to do that, we need to see how much dimension we need for the latent space here. And what we actually did is, in this 2D example, is that we try multiple space, 2-dimensional Euclidean space, 16 and 32, and then we see what is the trade-off. As we can see, if we increase more if you increase larger dimension latent space, I can get more details performance, and then my loss will go down. But if I actually keep adding it, there's a diminished return on adding more dimension to representing the data. You can also find that in a linear method, like singular-value decomposition. The only difference is that in the graph case, the compaction is not, the dimensional reduction is not conducted in a linear manner, but in a nonlinear manner. So this is the internal variable graph, and this is the reconstructions. The reconstruction are using a vector. So what it translates to is that if I'm giving you the right vector, I should be able to map it back into the physical representation that are originally in the graph. And from the graph, I can map it back into a finite element solutions. So you can see there's some difference in the 16 dimensions, but if I actually allow 16 different bases, I can already pretty much represent all the stress strength relationships that are involved. I will get a local pattern. You can see the same thing. If I increase the dimensions, I can do better, but then that improvement is actually more margin. Now, why do we need those internal variables? The reason is the following. We want to replace the descriptor. Now, this encode feature vector is perfect for the as a descriptor because of the availability of the decoder. We knowing that while we actually don't necessarily have the vocabulary to describe those revolutions, if I change the vector in the latent space, I can use the decoder to map it to a different pattern. And in other words, when I evolving the finite elements, if I actually representing it in the descriptor sense, what I actually see is just these 16 components of the vector evolving, and then I can actually using that 16 dimensions revolution to actually indirectly control a finite element that would have thousands or maybe million of degree of freedom if there's the dominant pattern is actually small. So we're using it in a level set plasticity setting. This is actually a U surface involved in time. Remember, in the first part of the lecture, we talked about a static U surface, but here we wanted to evolve with some internal variable. Okay, what basically we need to do is to connect these revolutions of the internal variable into a macroscopic plasticity model. And I would say that the implementations in this case, we don't use the manifold approach, but if you actually look into the details, this is very close to a classical plastic algorithm. And then we can actually seeing that we can evolve the, if we put it back into the return mapping algorithm, basically the revolutions of the internal of the encode feature vector, where we just simply predict it with RNN neural network or potentially other things such as new ODE. We can actually just using it as an additional constraint for the return mapping algorithm that predicting the stress. So this is actually one example of the solutions when we actually write the return mapping algorithm. For the first time, not only do we actually know the revolutions of the internal variable, but we know the pattern that are evolving. So this is, I think, is very interesting because in the sense that we are also running a reduced order model simulation of the finite element, but we are using a return mapping algorithm, constitutive law to actually evolving it, and then we have all the microstructure revolution available in a way that we just modeling the in a way that we just writing a material model. This is the time revolutions, and then this is the direct numerical simulation response corresponding to the return mapping constitutive law response with the access to the microstructure. And you can see that by controlling the feature in the very low dimensional vector space, I can actually get back the details of the deformations. This is also the case for the more complicated architecture, microstructure, and then we can also check that advantage of it is that we can actually also control the detail physics. In particular, we can in this example we can also ensuring that if the material is unloading, the internal variable is actually not evolving. So which is actually hard in a black box RNN setting because there's no speed on the elastic plastic thing, and then there's no internal variable that can be integrable. So the last questions, I think I'm almost running out of time, is that I want to talk a little bit about not just what we do with the data, but how we get the data. So if you notice that we need to write a very high dimensional model. This is, by the way, related to a project in the PSAP on the micromorphic continuum, where we need to write a micromorphic U surface that are very high dimensions. But here, what we want to think about is the relay questions. In real life, when we try to get the data, we actually need money to do it because we need a physical experiment or MD simulations or dislocation dynamic. But anyway, those time and effort are finite. How do we actually use as little data as possible to create a good model? So the experiment itself here could be represented by Marcus' decision process. We can think about experiment as situations where we continuously try to continuously perform different tests, and then it has a reward. I won't go over the details because I think I'm running out of time, but what I actually want to talk about is that in our new work where we try to use machine learning, a type of machine learning, the deep reinforcement learning, to design where do we want, what kind of loading path do I need to create a specific load model. We can actually also take advantage of our representations of the state. In particular, in the MOOC0 that are published in Google DeepMind, the deep reinforcement learning contain 3 different neural networks. The prediction neural network to tell you what is the policy value to do something, to create actions. A dynamic network that require us to actually simulate the environment, and a representation network that can turn the observations into a state where we actually decide what to do next. So the graph here could be also used as a representation of the state. In particular, in this DEM example, the material are actually loaded, and then there's in the granular material, the normal force and then the tangential force would actually lead to can be represented by a node weight and an edge weight graph. Here we will use the published data paper in 2018, the crystal graph convolution neural network, to converge the weight graph into a new graph that doesn't have the edge weight, and then we embedding it into a vector. These vectors are actually used to provide the perceptions of the machine learning model. And then I think I'm running out of time, but I would like to show some of the results here. We're basically using it for several purposes. One is to check what type of data we need in the parametric space. Where do I put those data? Another one is to check what is the weakness of the model. So this is actually a very simple test. We test the black box model with very simple vanilla LSTM, if this is the right terminology. And then we basically have a lot of checks and separation, the deformation to create a database, and train the long short-term memory layer to replicate the stress string behavior. You can see that on the surface, the LSTM can provide some very good response. But if you look at we can also use the reinforcement learning to find out the weakness. This is the actual weakness of the LSTM simulation. You can see that despite of the fact that you can capture a lot of good behavior, somehow if you're loading it in this specific way, just loading, unloading in a very boring, elastic manner, you can actually get this buckling due to the overfeeding. And what we actually see here is that incorporating the graph as the perceptions as the representation network can actually reduce the number of try and error. Without it, we need about 10K of training step, but with a better state, we can cut it to 450, which is actually a gigantic improvement in terms of the need for explorations. I think I'm already, I hope I'm not going too fast, but our conclusion is the following. In the big picture sense, what we're trying to do is the following. We want to see whether we can come up with a new type of model that are not only able to explain the physics, but quantitatively represent the solid mechanics behavior in a predictive manner, but in a very precise sense. So precision is what we're trying to achieve in this line of research, and precision requires us to actually thinking about all those details about the manipulating the geometry and evolving it in a particular parametric space. And we actually found that the machine learning tools that we actually pick actually quite handy in tackling those problems. And also for that, we also seeing that the efficiency and the values of the data are actually really depends on how we actually are representing it. So in the machine learning world, we have all those things about a very high dimensional problem. We conduct a representation learning, and then from that we build a model to doing it. We're basically following this great grand recipe, but apply it to a mechanics problem. I want to thank the sponsor of the past and in the current. And then I, of course, want to thank my student and my collaborator that inspired us to perform this research. And I want to thank the audience for the patience to listen to my talk and for all the questions that they may have. Yeah, please feel free to ask me any questions. I hope I'm not too running out of time. So.
No. You're good. Thank you so much, Steve, for that wonderful seminar. So we'll open up the floor to questions. So you can raise your hand on Zoom, or you can type your question and we can redirect them to the speaker. Any questions for the speaker? Okay. So Stephanie Taylor in the chat's asking, out of curiosity, what are the timescales that you're evolving your plasticity models on?
Oh yeah, this is actually interesting. So the plasticity model itself is way independent. So it doesn't really involve a time scale. However, in the level set paper that we use, it does involve an ad hoc time scale, which is a cumulative plastic strength, because both the real time and then the cumulative plastic strength is monotonically increasing. So this could be used as, so we can actually using it for just for convenience to evolve the U surface in the Hamiltonian Jacobi equations. So anyway, so what we actually try in this set of tests, all the plasticity model, all the plasticity problem are way independent.
Okay. All right. So Suku has a question. Suku, please go for it.
Yeah, hi, very nice talk, Steve. So I had a question on the patches that you put together, right?
Yeah.
So on each patch, you have a different neural network?
Yeah.
Okay, and then you're gluing it together, right?
Yeah, exactly. It's
right?
like, yes, you probably get the
yeah, so I don't know if it was like probably a slide 12 or so. I don't know where that, I saw something which was familiar, right? On slide 12.
Yeah, let me.
The entropy slide.
Yeah.
Because that seemed very similar to Maxent, actually.
Yeah. Actually, there's a connection to that. Actually, absolutely.
Because you have like the first term is like the internal energy, and then you have entropy, and then your term, I forgot what it was, gamma or something, right?
Yeah, exactly. Actually, you can think about it as you maximizing the. Let me explain it a little more.
So maximizing the relative entropy, for example, right?
Yeah, exactly. I always worry
that one, right?
I always worry that I go too slow. So, but if
so it's exactly that. You know, if you go back to like Marino's and Michael's paper, right? For example.
Exactly.
Yeah,
that's
so it's exactly that, right? I mean,
exactly.
So the related question was, how do you ensure that the approximation, how do the patches glue together? Because each is an independent approximation, right? What you have is like a domain decomposition kind of strategy, right?
Yeah, exactly. That's the point.
And then you glue it together, but how do you ensure that the patches match, basically?
So you need to define the sense of match. Basically, we train the individual patch first, and then we retrain it again to ensure that the patch are glued together with these criteria as the loss functions, as this one.
Yeah, so just weekly you're enforcing it, right?
Yeah, weekly and both, but more in the so it's more on the sense of making sure that they are in the same locations. So for different patch, for the same point, they are in the same locations, and then also the same orientations of the gradient. So these two criteria. And this is actually after the synchron loss functions is actually enforced. So you train it 2 times. One is that you're training the individual patch first, and then you enforcing and then you correct it like you predict, and then you're matching it together.
Yeah, one last question is that you're using ReLU, right? Here.
Sorry,
you're using ReLU, right, as the activation function. Yeah, so ReLU will give you only C0, right? Because by definition, it's not smooth. So
yeah, but I will add the gradient term here.
Okay, so you regularize it with the entropy part, right?
So what I want to show, this one is
okay.
The one, by the way, this idea is not coming from the multi-patch one, is coming from a computer graphic, coming from the author Francis Williams. By the way, our paper has published. But then they want to represent a really compact object like a furniture or something geometrically really complicated. And what they did is that they found out that the local approach is actually more flexible, which is obvious because you don't, instead of creating one really complex object with one mapping, it's easier to have a local region and then you map something very simple and then patching it together. Just like a finite element, individual finite element have very simple deformations field, but then combining it, you can form something really complicated. So here we just follow that idea.
Okay, thanks.
Yeah, and then thank you. And also this one in the paper we explain it a little bit more. Sometimes for some applications you may not need the same revolutions for the same stress. Like if I actually want to, if I know that I need to design a build low bearing system that have a lot of bending, I may want to put more resolutions in the direct numerical simulation on the bending mode, but then compaction may not be that important. And then this patch approach can allow us to have different resolution for the thing that I need more high accuracy.
Okay. So Ronak Shogi has a question, Steve. So how do you define number of patches and how many patches were needed? Just 6?
Yeah, we need more than 6, and then there's a few criteria. So this is a hyperparameter. Obviously, if you have more patch, you need more neural network, but you can also control it. This is something that we need to use as an input, and then you need to anticipate how complex the geometry is to design the right patch. In our case, I think that we never use anything smaller than 32. But that depends on the need. For the 1 meters, you really don't need that much, as you can see here. If you have less patch, in principle, you can actually put the burden onto the local mapping, but then you need to learn a more complex mapping. So, and also, I want to mention that there's also another thing that we need to think about is that if there's no guarantee that all the patch would create a closure. Which could also be a problem. In this case, we have a closure so that we know that the object is actually closed. But in the 1 meters case, that there shouldn't be any closure because that cylindrical object go infinite into the infinite directions. So this is actually something that could be a limitations of this approach. It's actually better for the material property that for the parametric space that have a closure. If you anticipate a half space, then it won't be as efficient. So like the 1 meters, it doesn't depend on the mean patcher, right? So this can't go to infinite, and then but then your patch is finite. So anyway, this is one of those things. But in general, you can always find a parametric space that actually create a closures. So.
Okay, thanks for all those questions. Any other questions or the speaker? Professor Sun?
Probably if anyone, no one else is there, I can ask one more.
Yes, Suku, please. Yeah.
Sure, yeah.
So I can talk to you afterwards, of course.
Yeah.
The other question was, I mean, did you check also with, depending on the architecture, like how many depth and width of the network? I mean, do you get convergence, or I mean, if you change the, the number of neurons, basically, right?
Yeah. Oh, you mean do I tune the hyperparameter?
Yeah, if you change the hyperparameters, then do you have to play around with that, or you get pretty much the same result? Or
if you tune the hyperparameter, you will get different results. But then I would argue that for example, for the multi-patch approach, I would argue that you probably have an easier time to tune the. So basically, the idea is that this is a very complex problem. Instead of training one magical neural network that can create all the mapping, I actually break it down into a smaller problem so that I can ease the pain of have to fine tune the hyperparameter. But even in that case, we do need to train the hyperparameter. That being said, I did not individually tune the hyperparameter for each hyperparameter, or more accurately, I don't think my students have tuned all the hyperparameter for each individual patch, simply because I can address the complexity by reducing the size of the patch to make sure that individually the complexity are roughly similar. You can also change it multiple times, but then this is one of the important questions. Instead of choosing one difficult problem, I want to break it down to something as simple as possible. But hyperparameter always affect the neural network performance.
Yeah. Okay. Thanks a lot.
Yeah, I agree. Yeah.
Okay. Any other questions for Professor Sun? If not, we are exactly. So Jose Alves is saying they would like to go through the references. If you can provide them.
I can. If you can give me 1 minute, I can find the paper. Actually, in our in our web page. So I have research web page, and then that actually provide all the information. But then the paper is actually also the multi-patch paper are already available, and I'm hoping that at some point this could be the paper is actually here that actually provide more details on the multi-patch approach. And then for the graph, we just get back a review yesterday, so I think that if I did not write the response letter in a manner that trigger another review, maybe we will get it done very soon. So yeah, but the information are there. So oh, and also, sorry, one more thing is that maybe I do a little bit of advertisement. So we actually also have a short course that actually provide more details. Let me see whether I can find the informations. So yeah, so we also provide some basic software in our research group web page, and then in the WCCM and in previously I have also I provide the course training. So there are longer versions of this lecture that you can find out the information, or you can directly contact me.
All right. Thanks everyone for those questions, and let's thank Professor Sun again for that wonderful talk. Thank you very much.
Thank you for your patience. Thank you for your time.